Hello, friends. You're recording the meeting. Hello, friends. Does this work? It does. Who am I? My name's David Carlin. I work for Afterpay on a product called Money by Afterpay. But my company, Afterpay, was just acquired by Block, which was formerly called Square. And we've got something to do with a cash app. And so I don't really know who I work for anymore, but one of these entities pays me money and I work for them, and it's great fun. So you should come and work with me because we are hiring senior Ruby, iOS, Android devs. So ping me if you're interested. Image compression. So why am I talking about image compression? Why should you care? I think this is an important problem because it's kind of integral to what we do as web developers. And no one really seems to know who owns this problem or to know much about it. So as an engineer, I've always assumed that designers take care of this, right? Like they give you the images, the assets, you just plonk them in the website, call it done. But turns out designers don't really know much about it. They just export stuff from Photoshop and give it to you and expect you to make it ready for the web through compression or something. So it seems to be a problem that's fallen in the cracks and no one takes ownership over it. So I thought I should learn a little bit about it. So most websites contain a lot of images, and poorly compressed images can make your website slow, and no one likes a slow website. So there's two main types of compression. There's lossy and lossless compression. By the names, you can probably guess what they are. So lossy compression throws away data that it thinks isn't important for the end result, creating smaller file sizes. So this is like JPEG, throws away image data, MP3, throws away audio data, MP4, video data. Lossless compression, as you can probably guess by the name, doesn't throw away any data. So the decompressed file at the end is identical to the file that you've input. You imagine, you're doing an assignment for school or uni and you type up 2,000 words and then you zip it up and you send it to your teacher. When they unzip it, you expect it to be the same file. You don't expect like the compression algorithm to just throw out some of the words that it thinks was unimportant. So this is like lossless. What goes in is what comes out. It's like zip file, like PNG. So those are your two main forms. Where am I? Common image formats. You've probably heard of some of these, some of them maybe not. JPEG. JPEG is everywhere. You'd be lucky to spend a minute on the internet without seeing a JPEG image. It's lossy. It's introduced in 1992. It's been around a long time, very popular. PNG, on the other hand, lossless, introduced in the late 90s. It's also very popular. So WebP was introduced by Google in 2010. It really struggled to get widespread support. Safari's just added support in 2021. And this seems to be a common problem in the introduction of new formats. A lot of smart people spend a lot of time making these amazing new formats, and then they release them and they present them to the world. And it usually takes a decade or more before they become widely used. So everything moves very slowly, but over time things get better. AVIF is the new kid on the block. It's got fantastic compression ratios, a lot of real smarts in it, but it takes a lot of processing power to encode and decode. And also, it's not widely supported yet. It was just introduced a couple of years ago. I expect over the next 10 years, we might see a lot more AVIF images. So originally I was thinking I could do a deep dive into all of these and say how they work and what algorithm they use. And then I thought, geez, that's a lot of content. Also, that's a lot of preparation. As you can see from my slides, I'm not really one for a lot of preparation. So I'm just going to stick to one of them today. And I'm going to stick with JPEG because it's everywhere. The techniques that it uses are used everywhere. So a lot of the other image compression algorithms, lossy image compression algorithms, use the same sort of techniques, but just in slightly different ways. And also because it's lossy, the algorithm's just a bit more interesting because it has to have some smarts in it where it decides what it's going to throw away. So let's start looking at the human eye. So the human eye has these cone cells in them, which are sensitive to light. And I don't know exactly how it works, but light stimulates them and they put electrical signals through to the optical nerve, something, dot, 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 you see things. And so you have three types of these cone cells that detects different wavelengths. And as you can see from the graph here, two of them, these two here, they see green pretty well. And this means that we see green twice as well as we see any other color. And, they say that from our ancestors, cavemen, whatever, probably spent a lot of time looking at green stuff. They were probably out in forests and grasslands, and it was very important to their survival to be able to spot the right shade of green for the leaf that was right to eat, or I don't know what, but green was advantageous to human survival. And so we've evolved to see green really well. So what about in computers? Computers, in an uncompressed form, images in computers are just a grid of pixels. And it's in the red, green, blue color space. So you have a value for red, a value for green, a value for blue for each pixel of an image. 0 to 255 is about 1 byte per color pixel. And because there's 3 of them, that's 3 bytes per pixel. So you imagine you have a 1 megapixel image, it's 1 million pixels, 3 bytes per pixel, it's 3 megabytes for a 1 megapixel image, which is quite a lot of data, which is kind of why image compression is so important. What about digital cameras? So where most images come from, say you've got a camera in your phone, it has a sensor in it, and the sensor has millions of these little light cavities or photosites. But as we saw with the computers, each little pixel has 3 colors, a value for red, a value for green, a value for blue. But in your camera sensor, it can only sense 1 color for each cavity, which turns into a pixel. So it does this thing where it sort of intersperses all the colors in the grid. And then it uses a technique called demosaicing, where, so if you look at this like red square here, the bottom left, it needs to figure out how much green is here and how much blue is here. And what it does is it looks at the sensors on either side, and it says, averages out these 4 things and says, that's approximately how much green I would guess is here. Looks at the blues around it and says, all right, I would average them out and say that's how much blue I could expect in this spot. And so the camera does this automatically. So at the end, you get your JPEG with all of your pixel RGB values, but from the sensor, it has to do a bit of magic to figure out what those values are. If you're using a digital SLR, you can get you can shoot in RAW and get a RAW format image, which hasn't done this demosaicing. And you can load that up in your computer, in Photoshop, in GIMP, or whatever you use. And you can use the demosaicing algorithms in Photoshop or whatever, which some people say are better than the algorithms that they do inside the camera. So that's a thing. And as you can see in this, there's actually more green than there is blue or red. There's twice as much green because we're so sensitive to green. Anyway, so that's a little side mission, but let's get to JPEG. The human eye is better at seeing changes in brightness than it is at seeing changes in color. And JPEG takes advantage of this. So up to now, I've been talking about things in the red, green, blue color space, but JPEG actually converts it to a different color space. You might have heard with like printers, they use YCYMK, is that right? So there's multiple different color spaces, and JPEG uses one called YCBCR. Now, Y is the luminance, which is like the brightness. CB is your chroma blue, or the blue part of the color spectrum, and CR is the red part of the color spectrum. And so because the human eye is better at seeing changes in brightness than it is at seeing changes in colors, it says this brightness channel here is more important. So if I store this at full resolution and then I downsample these ones, it's called chroma-subsampling because you're storing these at a lower resolution. You can save some size in your compression without really making it too noticeable for the human eye. So for every 4 pixels of blue, it might only store 1 value. And for every 4 pixels of red, it might only store 1 value. And so you cut down a third of the size already. All right, so take a breath here because that's probably the easy part. And we're going to get into the hard part now, which is discrete cosine transform. DCT for short. Firstly, some maths. Who remembers sine, cos, and tan from high school maths? Yeah. Well, SOHCAHTOA. Do you ever say SOHCAHTOA? We said that a lot. So cosine of an angle equals the adjacent over the hypotenuse. And I think you use that as a way of figuring, if you know 2 of these, you can figure out the third one or something. I don't know. Anyway, people use it for things. But for our purpose, it creates this nice little graph down here, which is the cosine graph, cosine of x. So we can say the cosine of a certain number times x, 0x, 1x, 2x, 3x, 4x, 5x, 6x, 7x. And 0, cosine of 0 is all at 1. Cosine of x is this, what we saw. And so as it gets a higher number, this gets a higher frequency. And so represented as images here, this would be all white, as you can see on the left here. This would be all white to black, as you can see here. White to black to white, white to black to white to black. Anyway, as you can see, these are the image representations of these graphs. So you've got this in the vertical, you've got this with the horizontal lines, and then you've got all these like crisscross interpolations between the 2 of them. Cool, right? Well, this is something that we use when doing the DCT. But just put that in your back pocket for a second. We'll use this in a second. Discrete cosine transform, it takes your original source image and it splits it into 8 pixel by 8 pixel blocks, working 1 channel at a time. So, imagine we're just taking the luminance channel. And then for each of those 8 pixel by 8 pixel blocks, it writes that as a weighted sum of these predefined cosine images. Right? So it's saying it's so much of this one plus so much of this one plus so much of this one plus so much of this one. You add them all together and you get back to the original 8 pixel by 8 pixel block. Great, right? You get these DCT coefficients. Now I know what you're thinking. Why the hell would you want to do this? What is the purpose? And the purpose is that for most images, the high frequency changes, which are the ones in the bottom right here, firstly, they're not very common in images. And secondly, we don't see them very well. So they aren't as important to the image. And so instead of all of the important numbers being randomly spread over this whole 8 by 8 grid, it moves all of the important numbers towards the top left, right? And this is important because when you want to compress something, moving all the important bits to one spot and all the unimportant bits somewhere else allows you to compress things better. Like hypothetically, we could just send the first 4 by 4 or 5 by 5 grid, and it would still make an image that looks essentially like the original. So that's just quick summary. You do these 8 by 8 blocks, you write weighted sums of all these cosine images until you have these DCT coefficients. Now, the next step is called quantization. And so you have a quantization table. So starting from here, we already know that the most important values are in the top left, but there might be some other values in the bottom right. But we want to, I guess, downscale them a little bit, limit them, quantize them a little bit. And so you have this quantization table, and you take your original table and you divide each one by its corresponding number in this quantization table. And these quantization tables are in the JPEG standard. And you know, when you go to export something as JPEG and it says what quality do you want to save it as, and you might save it as 90% or 70% or something. Each one of those percents corresponds to a different quantization table. It's saying, how much am I going to cut down these numbers by? So if you divide the 150 by 1, you get 150 because that's an important number because it's in the top left. But once you start getting over here, it starts dividing it by 4 or whatever, and becomes takes up less. And so what happens is you end up getting an awful lot of zeros in this bottom right side of the quantized coefficients. Right. What is the value in having a bunch of zeros over here? The value is that you can compress a bunch of zeros together pretty easily. So you arrange the numbers in a list with this zigzag crisscross pattern, which puts all of your non-zero numbers, or most of them, at the start, and at the end, you have a lot of zeros. Now, when you have a lot of zeros, you can use a thing called run length encoding to compress it. So it uses a slightly more complex compression, but at a simple thing, it would be like saying, instead of having 10 zeros where you write 0, 0, 0, 0, 0, 0, 0, 0, 0, you just say, and then there's 10 zeros, and then there's a 1, and then there's 15 zeros, and then there's a 2. So this compresses it. Whew. All right, big breath. Summary. You change your color space to YCBCR. You do chroma-subsampling on the chroma, CB and CR, to store less color information. And then you DCT. You split it into 8 by 8 blocks. You write each block as a weighted sum of the predefined cosine images. Ooh, hang on. Back. You do the quantizing, so you divide by the predefined quantized table to reduce high frequency changes. Then you use the zigzag pattern to put most of the non-zero numbers together. And then you use a lossless compression to compress that all together. Whew. JPEG. And that's one of the easy image compression formats. So yeah, that's it. Give me your questions.
Do we have a live coding example of you compressing it?
No.
Question. Thank you, David. That was great. I've kind of vaguely heard bits and pieces of this before, but kind of just to hear the whole journey was cool. Have you given all of these things, you could reverse engineer this to make them least compressible image out there. Are there examples of kind of like images that are really hard to compress because they fit all the characteristics that you don't want them to fit?
Yeah, so I mean, if you've seen a JPEG image which has a lot of artifacts in it, which is where you'll see it's generally let me it's usually like with solid lines. So yeah, you see something like this, and this is something that JPEG really struggles to compress. because it has a solid line in the original, which JPEG suffers or fails to compress very well. And that's because the assumption that JPEG works under is that a high frequency change isn't so important. And a sudden change from black to white counts as a high frequency change. If we go back to these images, maybe these ones are better. You don't really have one that's like white halfway across and then suddenly turns black. It optimizes for things that gradually change from one color to another. So to have an image that compresses poorly with JPEG, you just have to have a lot of solid lines in it that shift from one color to the next color. Whereas JPEG works really well as like, like photographs where colors change gradually.
Interesting.
But I mean, to counter that, like PNG is really good at compressing things that have solid lines in them.
Is there like a lossy format that is kind of like the opposite of JPEG, like a PNG but on lossy type stuff?
There's not, but you can actually do some pre-processing for PNGs to make it. You can do some lossy pre-processing to make PNGs compress better. So, yeah, like for example, PNG, if you have fewer than, I think it's 256 colors in it, it turns to a palette mode. So instead of having like the full, 255 or 3 byte for a pixel storage, it just works off a palette of 1 byte things. So there's a few other things that can make PNGs lossy, but it doesn't actually happen in the PNG part. It happens as like a pre-processing step.
Cool.
Anyway, that's it. Any other questions? Hit me up.
I mean, I don't know much about math, and I think that's just crazy the way like they got from point A to point B, like, and then with the zigzag, like how they're like, oh, we'll just like zigzag across, like.
Yeah, it's a pretty complex algorithm, but I think like in general, the idea is to take something that's sort of random and transform it into a way where it's not as random. So like the big numbers are at one end of the array and the small numbers are at the other end.
Cool. So
check, but there are lossy algorithms that can be used for PNG.
Okay, cool.
There's multiple algorithms that are available, and it's kind of adaptive, so it'll choose based on some preferences that you may have set. If you're doing a output, it may choose between the different algorithms that are available.
Okay. I feel like one big question is left unanswered, David. So who should care about, like, who should do the compression? The designer or the web developer?
I don't know who should do it, but I think it's as engineers, we should not just keep our heads down on the code, and we should have a holistic view of the product and the user experience that we're giving to our customers. We should make sure that the images that get onto the site are compressed at some point.
So interesting question from you, Kevin. I kind of feel that the framework should look after it. And I was listening to a podcast from the JavaScript side of the divide, and they've got this thing called NextJS, which is from what I understand, a static site generator with sprinkles of being able to do functions on the back end and React on the front end and lots of built-in stuff, which sounds like it would be a Rails competitor, but potentially even better in some respects. So one of the things they've released in one of their latest versions is they've got this whole thing about an image tag. So you just put an image tag in there. And I can't remember, David, what you said was the latest version of images, AVIP or whatever it was. So they already have support for that. So you basically just say, hey, I want to use WebP when I can, AVIP when I can, etc. It compresses it down to the right size for the page it's going to generate.
Yeah.
And also they've got smarts in there that you literally put an image tag in and it can give you like a fuzzy, very small image first and then transition out of it. And if you were to do that in Rails, or if you were to do that anyway, I need some kind of library to do it, or write the library or whatever. It's built into NextJS. So you literally just put in an image tag and it does that for you, is my understanding. Which is kind of cool, because then you don't have to worry about the nitty-gritty of network, transfers and how big's your page, etc., because the framework looks after you. But I think these things kind of come around and go around. Like at one point you'll say NextJS does all the right things, and in 2 years' time they'll be going like, we need the engineers that know how this works because nothing's doing the right thing.
I think the thing is like, that would probably get you like 80 or 90% of the way there. But at the end of the day, image compression is a bit more of an art. Like you're taking away visual data and you're saying this image looks good enough for the position that I'm putting it in. And, like this has happened a lot in my workplaces where like designers are like, oh, you want me to compress the images? Like what settings do I have to do to compress them? And you're like, well, you really have to say, at what point does the image look not good enough? And then make it a little bit better than that. And it takes a human to make that judgment, I think.
Cool. Yeah, I guess like if you're doing it, or like if it's done, with the person that deals with the website, and you can kind of iterate over that faster. It can just be, oh, that looks terrible. Okay, I'll just turn 10% up, and try that.
Yeah, so some images you can really compress the hell out of them and they look good enough, and other images like start looking bad a lot earlier.
Interesting.
I saw a great talk a few months ago. I can't find it now, but of like there's these like hosted services that you can upload your image to, like your whole image library, and then depending on where you need that image to be displayed, you can like ask for that image at a particular quality level and particular size. And like they handle all the like resizing and compression and everything, just give you the image back simply by putting parameters into your URL.
Yeah, and they provide, you're right. And they provide like if it's on mobile, it's like a much smaller version than if it's on
exactly. So it loads way faster depending on where you are.
Nice. A fun space to be in, that's for sure. Michael is asking if block is just a more compressed version of square. DC.
I don't think it's decompressed, right? It's gone to 3 dimensions.
Cool.